Hey guys, today we're going to be talking about two-dimensional or 2D materials. Now, I know what you're saying. That's impossible. We live in a 3D world. No material is 2D. And you will be correct. The 2D materials I'll be talking about today range from one atom to several atoms in thickness, essentially making them two-dimensional. The way I'll be demonstrating that today is using a sheet of paper. Now, when we have a stack of paper, it has a substantial width, height, and thickness. But when we take a singular sheet of paper, the thickness is insignificant when compared to the width and the height or length or whatever. Okay. As you can imagine, forming these materials is not as easy as pulling a piece of paper off a stack. Manufacture of 2D materials only started in 2004 with the isolation of graphene, which is an atomically thin layer of carbon arranged in a hexagonal lattice. Graphene is the 2D version of graphite, a material commonly used in pencil lead. Since 2004, many other 2D materials from across the periodic table have been isolated and studied. Graphene, however, has remained dominant due in part to its unmatched carrier mobility, which essentially means that it can move electrons around really fast. This property means that any electronic device utilizing graphene will have an extremely rapid response to stimuli and also an extremely rapid recovery once the stimuli is removed, both of which are equally important. One application where this is especially useful is gas sensors. We need the sensor to be able to alert us quickly if a toxic gas is present, and alert us just as quickly when the toxic gas is no longer present. Current gas sensors have a relatively sluggish response time, which gas sensors construction from 2D materials project to vastly improve upon due to the aforementioned carrier mobility. In certain situations which require a rapid response, an improvement in response time of a couple seconds can be very meaningful. So to give you a better understanding of these sensors, I'm going to demonstrate the mechanism through which they work. Now, there are many different combinations of 2D materials which could be applied as a gas sensor, but right now two types seem especially promising. Those two types are TMD and graphene, and then a TMO and graphene. Each is composed of an atomically thin layer of the TMD or TMO on top of a singular layer of graphene. TMD stands for transition metal dichalcogenide, and some common examples are molybdenum disulfide, tungsten disulfide, and molybdenum diselenide. Now, you don't really have to understand what a TMD is. You just have to be able to associate TMD sensor with this particular mechanism to understand how it works. So, to demonstrate our sensor, this is going to be our graphene, and then this is going to be our TMD. So we have our layer of graphene underneath, and then our TMD on top. So what's going to happen here, so this is going to be exposed to the atmosphere where we want to measure the gas, and we have our target gas, which is going to be represented by our ball here. So our target gas is going to be floating along in the atmosphere, and then it's going to come in here, it's going to come between these two layers, and it's going to adsorb onto the graphene. And when it adsorbs onto the graphene, that's going to change how electrons move around in the structure here, so that's going to change the resistivity. And then that resistivity that changes in the structure here is going to get interpreted downstream by other parts of the sensor, and that's going to be interpreted as the presence of our target gas. And then our next type of sensor is our TMO graphene sensor, and TMO stands for transition metal oxide, and common metals are zinc dioxide and manganese dioxide. So again, we have our graphene on the bottom, and then we replace our TMD layer with the TMO layer. So the way this one works is a little different. It's exposed to the atmosphere, and obviously there's a lot of oxygen molecules in the atmosphere. So our oxygen molecules are going to come along. It's a diatomic molecule, so we have two oxygens here in one molecule. It's going to come here, it's going to cleave into two separate oxygen ions, and then those are going to both adsorb separately onto the surface of the graphene. And then our target gas molecule here is going to come along, and it's going to either oxidize or reduce these oxygen ions here, and that's going to change the resistivity, and that will be interpreted downstream as the presence of the target gas. And then the target gas just floats along. It doesn't actually adsorb onto these oxygens as with the TMD gas sensor. It just moves through the sensor and moves along downstream. So to summarize each mechanism, for the TMD and graphene sensor, we have our gas molecule, our target gas molecule. It comes in between the layers, adsorbs onto the surface of the graphene, which changes the resistance of our structure, which is interpreted by the computer bits of our sensor as the presence of a gas. And then for the TMO graphene structure, we first have the oxygen molecules splitting, ionizing, and adsorbing onto the surface of the graphene. Then the target gas molecule comes along and reduces or oxidizes these oxygen ions, and then that changes the resistivity of the structure, which is again interpreted as the presence of a gas. The differences between these mechanisms are not trivial. One can imagine that because of the differences, each sensor type is more suitable for different gases. Sensors can be tailored to fit a specific application. Some gases will tend to absorb onto graphene more readily than they would react with an oxygen ion, in which case a TMD sensor would be preferred, or vice versa. Now, the view of these mechanisms that I gave you was a very broad view. The actual mechanisms are a complex set of steps involving mass transfer, chemical reactions, and movement of electrons. It is important to remember how complex these mechanisms actually are because the complexity makes them delicate. A small imperfection can render the sensor completely inoperable, or worse, make it produce false readings. Gas sensors constructed from 2D materials are compact, highly sensitive, and have an unparalleled response time. But the reason you're not seeing them in mass production is because of how difficult it is to manufacture these 2D materials necessary for constructing a sensor. The processes we have now are expensive and not scalable to the level of a manufacturing plant, which means that in the foreseeable future, these types of sensors will not be seen in mass production. There is a possibility that they prove useful enough in extremely specific applications, such as medical or military, for the cost to be worth it. But you aren't going to be seeing one of these in your home anytime soon. We'll give it a decade or so. That about wraps it up for today, guys. Hope you all learned something interesting. But regardless, this is Gavin Courtright bidding you farewell and adieu.